Lee, and I'm going to be presenting Lab 2. So for the introduction, the purpose of this lab is for the students to observe an object falling from the state of rest. And to do this, the students will use tracker to plot the data of a falling object in relation to the height and time, and using the glow script, we'll plot the predicted graph. And the main principle used is the Newton's second law, as like the previous lab, and the equations used are the net force is equal to vector, and where the y component is affected by the gravity, and the ball mass times gravity plus the constant times the ball velocity of y and times the ball velocity of y, and that is the F net for the effects by gravity and drag. And just for the effects of gravity, the F net would be negative ball mass times gravity, and the ball velocity is equal to ball velocity times F net divided by ball mass times delta t, would be another equation used to update the velocity. And to update the position, it would be the position of the ball is equal to position of the ball plus ball velocity times the change in t. And over here demonstrates the preview of the results of the models with and without the drag. So basically the experiment, the initial conditions were the paper ball, which was 0.005 kilograms, and I used a paper ball instead of like maybe a solid or a rock to include drag in this experiment. And the ball was dropped from rest, and the falling distance of this was 0.914 meters, and you can see the data on the picture demonstrated right here. And the system was the paper ball, and the surrounding was the gravity and the drag. So to predict the position, so the code that we had to make for the computational without the drag was basically I just had to change the code for the ball mass, which is 0.005, and the position was not at 0.931 as mentioned previously, and the ball velocity was initially -1. And you can see that the net force equals only the effect by gravity, and which is mg, and the equation would be as explained before. This is to update the velocity, and this equation would be to update the position. And this is the graph that it made for without accounting for the effects of drag. And accounting for the drag, I basically changed the same initial value on the top, and just the only difference was in the net force, where the to counteract the effect of gravity, the effect of drag was accounted for, where the B was calculated by me to try to fit the baseline for what to the graph of what I have created in the observed graph, and we will demonstrate more in the next slide. Basically, so this is with the drag and this is without the drag. And the first graph with the drag, you can see that it fits the orange line is the observed model for both of these graphs, and you can see that with the drag, it really fits the model better, it really predicts it better, while without the drag, it shows that just the effect of gravity, because there's no counter force, it just falls a lot faster. So what does it mean? So which model predicts the terminal velocity? I believe that the model with the effect of gravity and the drag is what predicts the terminal velocity, because with the terminal velocity means that the net force is 0, and so if the object was initially thrown downwards instead of dropped from rest, to create the net zero, the drag force would have to increase to compensate for the increase in initial velocity, and that would be the difference. Thank you.